You know, in our endless quest for more power, it turns out we've hit a wall. But it's not the kind of wall you might think. It's not about resources. It's a wall of heat. And this invisible barrier, it's quietly shaping the future of, well, pretty much everything, from our cars to the cloud. So today, let's talk about the heat wall.
Yeah, that one sentence. It comes straight from the engineers who are right there on the front lines, and honestly, it just perfectly captures the entire challenge. It sounds so simple, right? But the implications, they are absolutely massive for our electrified world.
And this right here is the core misunderstanding that I think a lot of us have. We're all obsessed with generating more power, right? More solar panels, bigger wind turbines. But the real problem, the much harder problem, is actually how we handle all that power. How do we efficiently convert it, control it, and get it where it needs to go? That's where we hit the wall.
Okay, so let's give this thing a name and really dig into what we're up against.
So what is the heat wall? Well, maybe the best way to think about it is like a universal tax on power. I mean, every single time you switch, convert, or control electricity, you pay a little price. And that price is wasted energy that shows up as heat. Now, as our demand for more and more power in smaller and smaller spaces just keeps growing, that tax is becoming, frankly, crippling. And the consequences of paying this heat tax just cascade through every single design. To deal with all this heat, engineers have no choice but to add bigger heat sinks, these complex cooling systems. And what does that do? It adds weight, it adds cost, and it adds more components that can, and do, break. It even leads to this thing called derating. That's basically a fancy term for when a device can't actually perform at its advertised peak because it would literally overheat. So when you boil it all down, heat just erodes reliability and puts this hard ceiling on what's even possible.
And look, this isn't just some abstract problem for engineers to worry about. The heat wall is showing up everywhere. I mean, it's impacting the critical systems that you and I rely on every single day.
Think about electric vehicles. Heat is the #1 enemy of performance and range. Or what about fast chargers? Ever wonder why you can't just charge your car in 5 minutes? Well, a huge part of it is heat. The systems just can't handle that kind of thermal load. Then you've got our factories and warehouses. All that heat degrades the electronics that power industrial motors and robots. And that leads to unexpected failures, really expensive downtime, and these super complex maintenance schedules. Heck, even our main power grid is feeling the strain. When you're converting all that energy from solar farms or wind turbines to feed into the grid, you generate an enormous amount of heat. And that directly impacts the efficiency and the stability of our entire electrical infrastructure. But if there is one place where this crisis is happening right now, in real time, it's in our data centers. You could say they're the canary in the high-power coal mine.
I mean, data centers are feeling the squeeze from every single angle. A giant chunk of their power budget, it doesn't even go to computing, it goes to cooling. Get this, for a lot of the big hyperscale facilities, a staggering 40 cents of every single dollar spent on power is just to keep things from melting. Heat literally limits how many servers you can physically cram into a rack. It wears down and just destroys expensive hardware. And when you're operating at the scale, even a tiny inefficiency multiplies into a massive cost. The whole AI revolution we're saying, it runs on power. And right now, that power is hitting a thermal ceiling, hard.
So okay, if the problem is this big, what are we doing about it, right? Well, the industry has been fighting this war for years, but the entire approach might have a pretty fundamental flaw.
And don't get me wrong, some incredible ingenuity has gone into this fight. We've gotten better semiconductors, smarter packaging, really advanced liquid cooling, even some absolutely heroic software hacks to try and manage temperatures. All of that deserves a ton of credit, but they all share a common theme.
And here it is. Here's the flaw. Almost all of our solutions are about dealing with heat after it's already been created. We're either dissipating it, moving it somewhere else, or just trying to endure it. It's like we're getting much better at cleaning up the mess, but we're not actually stopping what's making the mess in the first place. This is where the story takes a really interesting turn. What if, instead of just managing the heat, you could fundamentally change the process that creates it? Well, that line of thinking has led to the development of something totally new, a whole new category of component.
And to be clear, we're not just talking about a slightly more efficient version of what we already have. No, this is a physically different way of doing the job of switching and controlling huge amounts of power.
So there's a company called FluxWorx, and they're developing what they call a magnetic transistor. It's a new category of component, and it's based on a patent-pending proprietary architecture and patent-pending proprietary switching. The whole idea is to attack that heat generation right at the source.
So think about it. If you can create less heat to begin with, you unlock this whole cascade of advantages across the entire system. Your systems can be smaller and lighter because you just don't need all that bulky cooling. Reliability shoots up because the components aren't constantly being stressed by high temperatures. You get to achieve higher usable power density, you cut down on maintenance, and, here's the big one, you ultimately lower the total cost of owning and running that system over its whole life.
So what does this all mean when you step back and look at the big picture? Well, the ability to finally break through that heat wall. It could change the entire equation for our electrified future.
And if there's one thing to take away from all this, it's this. In the world of high-power systems, cooler isn't just a nice-to-have feature. It's not about comfort. It is capability. Reducing heat directly unlocks performance, it unlocks potential, and it unlocks possibilities that were just completely off-limits before. It really is the fundamental principle here. You address the thermal constraints way down at the component level, and then everything built on top of that system just gets simpler, cheaper, and more reliable. It's a simple equation, but one that could completely redefine what's possible.
Because ultimately, tackling the heat wall, it's not just some engineering challenge. It's about enabling the entire next wave of electrification. We're talking about AI and data centers, electric vehicles, a stable green grid, doing it all in a way that's actually sustainable and efficient. It's about building a future that doesn't have to constantly fight a losing battle against its own waste heat.